Okay, so thanks to the organizer for inviting me to give this presentation. And as said in the title, I will try to give you an overview or some basic ideas on how to compute the four-wave interaction in discrete third-generation wave models, with a specific focus on the Gaussian quadrature method, so GQM in short, because it's a method which has a growing interest and which is developing. So this is a work I have been doing with some of my collaborators here, in particular with Elodie Gagné-Renou, who did her PhD almost 15 years ago now, and also based on discussion with other colleagues like Igor Lavronov, Sergei Baidulin, Herbrand van Vedder, and Fabrice, among others. Okay, so the outline. Well, I will briefly recall you, but it must be fresh in your mind. The kinetic equation after the presentation of Miguel and Nicolas, and then I will try to describe the basic principles of some of the methods, considering two approximate methods: the DIA and extension MDIA, and diffusion type approximations. And then I will focus on more exact methods, and what I will be calling reduced exact methods. I mean, starting from exact method, but using them with a reduced number of configuration. In a way, we deteriorate them a bit, I will say, to get approximate method. And among this family, I will speak about the WRT method and the GQM, as I said before. And then I will give you some examples and comparisons for application on the turning winged case before concluding. Okay, so the kinetic equation, okay, it's just this famous equation solved in our wave models. This is classical, with several source terms and transfer term on the right-hand side. N is the action density spectrum. This is classical. K is wave number. Sigma, the intrinsic angular frequency. And in general case, they are related with by the dispersion relation. And this equation is a generalization of the kinetic equation that was briefly presented by Miguel, derived by Klaus Hasselmann in the 62, where the evolution of the wave action density spectrum is governed by the nonlinear four-wave interaction term. Okay, and okay, so this the expression of this term was derived by Hasselmann and Sakharov, as already said, and it takes the form of a Boltzmann integral, and it describes, I recall you, weakly nonlinear interaction at third order. So you can see that by the cubic products of the action density here, and it's a six-fold integral. Okay, because each of these integral applies on the two components of the wave number vector. So you have kx and ky for this wave number vector, for this one and this one. So in total, this is a six-fold integral, so which is quite cumbersome to evaluate in practice. Fortunately, we will benefit from the presence of the Dirac delta function here, which will allow to decrease the number of integral from 6 to 3, as I will show you in a while. So here, G is a coupling coefficient. So I didn't write its expression here, but it can be found in several papers listed here. It's quite an involved expression, but it's explicit. So once it is coded, it can be used quite easily. And you have, as I said, the two resonance conditions, which restrict this machinery, I would say, to quadruplets which fulfill the two resonance conditions. So one over the wave number vectors, and one over the angular frequency, sigma. Okay. So as already said, only quadruplets of wave component which fulfill these two resonance conditions will exchange energy and momentum. Okay, and this, as is well known, this term is very important, in particular for governing the shape of the spectrum, because it transfers energy between quadruplets, and it governs the shape of the spectrum, the high frequency tail, etc. Okay, so the question now I will try to discuss in this presentation is how to, in practice, can we evaluate this integral. Okay, I will restrict here to deep water waves and pure gravity waves, so I don't consider any surface tension, so that the dispersion relationship reduced to sigma square equal gk. And it can be shown that in this case, for pure gravity waves, three wave interactions are not permitted. This is due to the shape of the relationship. The first order at which interaction appear is a third order for this four-wave interaction. And as already mentioned, we have this famous figure of 8, which describe the pattern that each quadruplet configuration may form to fulfill these two resonance conditions. Okay, so as I said, the numerical evaluation of this integral is quite challenging in reality because of the presence of the delta function, the six-fold integral here, and so it means a large number of possible configurations that will fulfill the two resonance conditions. And for that, there exists a number of methods which are called exact or nearly exact, which may provide reference results, but with large CPU times. So I mentioned here some of them. The first one being the exact NL code developed by Hasselmann and Hasselmann in the 80s, at the beginning of the 80s. And then we have the Webb ratio tracing method. The Japanese one called the RIAM method, the method from Polnikov, and also the method introduced by Lavronov in 2001, which is called now the Gaussian quadrature method. I will be presenting later. So this first class was mainly used for providing reference results, as I said before, but not operationally in wave models. For that, we have more approximate methods that can be employed, including the method from the DIA family, so discrete interaction approximation. I will come back to that later. So the original DIA, which has been the driver of all the wave model we are currently using due to its simplicity and its efficiency. It can be improved by considering several DIA type configuration with the MDIA. And then I will speak about diffusion type operators that were introduced by this author. And then, as I said, we can also think of using exact method with a limited number of configuration, and so reducing them, and so I call this reduced exact method. And in that family, I can include the area from Lin and Perry, the optimized GQM, which I will be calling the GQM row, of course, and also some recent improvement from the WRT proposed by Indian researchers. And I mentioned also here other approaches. I will not go into detail of this, but yeah, for completeness, you can find here the two-scale approximation from Reggio and Perry, for instance, and also the use of neural network that was introduced, for instance, by Hendrik Tolman a couple of years ago. But we may think nowadays, with the progress of machine learning and things like that, that this kind of approaches could come again on with more interest. Okay, I will be comparing the results of some of this method on a simple case. I took it from Hasselmann and Hasselmann. So it's a combination of a Jones-Swap type spectrum. You have the parameter here, and an angular spreading function of cosine at the power 4. So here you have a representation of the directional spectrum. So alpha of it, due to symmetry, of course you have the symmetrical part below, and the corresponding frequency spectrum. So I will compute, I will apply the various methods on this case, just to give you an idea, because we also have results from the exactNL code of Hasselmann and Hasselmann on this case. And yeah, it will serve me as a kind of illustrative example. Okay, I start with approximate method, and first with the DIA. The idea of the DIA is quite simple. Among all the possible interactions, configuration, Hasselmann et al. Only consider one particular configuration, which is assumed to be dominant, plus its image, so you can have the representation of it. So they choose only one particular configuration, which is defined in this way. So two of the wave numbers are equal, k1 equal to k2 equal k. And for the third component, sigma 3 is taken as 1 plus lambda times sigma. So sigma is the frequency associated with this k. And sigma 4 is taken as 1 minus lambda sigma, which I call sigma minus. And so when you put this into the two resonance conditions, you end up with this particular configuration where you have k1 here, k2, which is equal to k1. K3 is here. Okay, it has this angle. It is imposed, and by this condition and the resonance condition. And K4 is this vector. And so you have the image configuration in dot here. So only these two configurations are considered, which may appear as quite surprising because we are reducing a lot the original complexity of the integral. And we end up with this expression of the transfer term. So this is a transfer term for wave number k. This is for k minus, so k4 here, and this is for k plus, so k3. And so we get this expression, and there is a coefficient c here, which was tuned for approaching the exact computation. So this is very easy to implement, and it has high computational efficiency. And as I said, it was implemented in WAM first and then used in several other models. As I will show, well, it gives quite a crude approximation of the exact term. And so one natural idea after that was to try to sum several DIA type configurations, so adding more configurations. And here I show an example where 4 configurations are considered. So now we have 4 times 2 with the image each time configuration. Here I show the configuration proposed by Hendrik Tolman in 2004, for instance. And you have 2 parameters which are introduced, lambda and mu here, fulfilling this condition. And the interacting quadruplets are defined by these relationships. We end up with a similar expression for the transfer term of the 4 interacting wave components. And here I gave an example of the lambda and mu parameters associated with this proposition. So in this way, we have increased the number of configurations, which is still quite low, but we improve the estimation. So how does it look like? So on the case I just introduced before, this is a computation of the SNL term for the Jones-Webb spectrum I showed you before. Again, I only present the upper half, and by symmetry is the same below. So this is a reference result for the time being. So it's a result from the GQM fine method, but I will show you that WRT algorithm is giving the same. And so it shows you the frequency directional transfer term with positive lobe here below so the peak frequency is here at 0.3 hertz. So we have a positive peak here below the peak. We have negative peak here, and we have some slight positive lobe here, but quite low. And for this case, the corresponding DIA calculation gives you these results, where we can see some similarity. So we have also a negative peak here, but which is clearly more pronounced. And the positive peaks are somewhat different in terms of direction. In particular, this one is significantly larger. So it means that the DIA will tend to broaden the wave spectrum in comparison to the reference results. When I use the MDIA, so the extended version, you can see that we get a closer picture compared to the, I would say, reference calculation. The positive peaks looks better. And also this angular broadening here is reduced. Still, we have differences in the shape of this negative part. If I look at the directionally integrated term, so here I have plotted for reference the wave spectrum. So here we have the exact NL calculation taken from Hasselmann and Hasselmann in black with a black curve. And the DIA results in the red curve. So you can see what I mentioned before, a too large negative peak here, and the positive one, which is quite different from the reference result. And we have this additional positive lobe, which is also different from the reference solution. The MDIA in blue here does a better job, as you can see, with a blue curve, in particular for regarding the main peak here. But we still have differences in the negative lobe here. Okay, so this was for DIA. Another idea was proposed to approximate this transfer term by using a diffusion type operator. So this was introduced by several authors, among them Zakharov and Pushkarev and Polnikov. And so it's a, I would say, kind of heuristic approach based on the similarity of the effect of the transfer term with diffusion Laplacian type operator. So they propose to approximate the transfer term with this kind of formulation, where you can see a second derivative in frequency here and a second derivative in direction, so diffusion type operator, which applies to this quantity A, which is some power of the frequency spectrum times the frequency. So they have shown that this formulation, although quite heuristic, has some merits. In particular, it preserves some constant of motions, and it also admits solution of Kolmogorov-Zakharov type KZ, as does the kinetic equation. Sorry. So there is a coefficient here, which was tuned by Polnikov to this value. And well, this approach has some interest. In particular, it's quite easy to implement. There is no singularities, and we only have to compute second-order derivative in frequencies and direction. But this can be easily done by a finite difference scheme, for instance. So it's very computationally efficient. When we look, there are extensions of this method, which I call DE2 and DE3. They were revisited by Pushkarev et al. In 2004, and they came with the same expression of different expression, sorry, for A, and they replaced it by this expression, which is non-local, so which involves average value of F here, defined in this way. So there are two variants, which are a bit more, I would say, complicated than the first expression. And in the same case, in the same vein, we have tuning coefficient to determine, and there are values for that suggested in this reference. So when we look at the results of this approach is on the same case. So this is for the DE1, so the first diffusion method I just mentioned. The result of the four-wave interaction term, we can see, okay, a positive lobe here, a negative lobe here, and again a positive lobe here, which is, well, in a way, this one is not so bad, I would say, but here it's quite different from what we have in the exact calculation. The DE3 variant gives something which is quite similar in shape. When we look at the angular integrated transfer term, we get the orange curve for DE1 and the red one for DE3, which are not much different, in fact, on this case. And well, we can see positive lobe, negative lobe, and positive lobe, but which is in this area quite different from the exact calculation. Okay, so this was a flavor of approximate method. Now I move to exact and quasi-exact method with the WRT method. So in the WRT method and the RIA approximation, the idea is to make a more accurate evaluation of the transfer term. And so just to explain it in brief, so we have these 4 wave components interacting. So we will be computing the SNL term for this component, the component 1. So this one is held fixed. And we will be using the Dirac function on the wave number to obtain wave number 4. Okay, so we use the delta wave number function to obtain K4 as a function of the 3 other ones. So this one, I would say, is given from the 3 other ones. Okay, and now what we will be doing, we will integrate over all possible value of wave number 3. So the integral is simply rewritten in this way. So this is a transfer term for component 1. So as an integral over wave number 3 of this term, which I call T, which is a function of K1 and K3. So function of K1 and K3, okay? And so now K4 is given by that. And if we look at the expression of this term T, it reads like this. So it's the integral over wave number K2 of the coupling coefficient, it should be G here, sorry, the delta function on the frequencies, which I call it here W. So it's simply sigma 1 plus sigma 2, sorry, minus sigma 3 minus sigma 4, which is now a function of the 3 other wave number vectors. And so we have to integrate this over the wave, so a twofold integral over wave number vector K2. Okay, but we will benefit from this delta function to reduce the twofold integral to a one-fold integral. And this is done by integrating over a curve which is called a locus. In fact, if we maybe it's this term T. So this twofold integral, due to the presence of this delta here, can be reduced to a closed line integral over a curve, which is called a locus. And when we use that, so this term results in this term here. It's the inverse of the gradient of W. This, I will explain that later. So now we have to integrate along a line, a closed line, the locus, this term. And this locus is defined by W. W considers the function of K2 equal to 0. And so now, as I said before, the six-fold integral has become a three-fold integral. And so typical shape of this locus. So this locus is computed for each pair of K1 and K3. So as you remember, T is a function of K1 and K3. So here is an example. I choose vector K1 and K3, and I choose a number of here 32 points to draw the locus. So here we are in Kx, Ky, okay? And so this curve, this closed curve here, shows you the location of the wave number K2. So K2 covers this curve, okay? Due to the delta condition on the frequency, on sigma. Okay, and so we have to integrate. We have to calculate the integrand at each of these points and sum it. If I come back here, no, sorry, I move in this direction. Yeah, we have to discretize this locus with a limited number of points, and then we evaluate this term at each of these points, and we sum to get the t term. Okay, and this term has no singularity. And so if I sum up the double algorithm, so for each K1 component, for each K1 component, we define an integration grid for K3, which might be or not the same as K1. It can be different. In principle, it is different. And for each of these, or for each vector of this K3 grid, we compute the locus. So the curve, the figure of the egg-type figure I showed you just before, we compute it. And for each point, for each K2 on this locus, we compute the various terms, and we sum them. And then we sum the various contribution for each of the K3 vector of the grid. Okay? So that's the principle of the double RT methods. And in 1999, Lin and Perry proposed a reduced method based on this, called the reduced interaction approximation, where they restrict the integration over K3 locally around K1. For that, they define a grid of limited extent, as you can see, in terms of wave number, ranging from 0.5 K1 to 1.7 K1 in terms of magnitude, and an angular sector from minus 45 degrees to plus 45 degrees with respect to the direction of K1. So it's a local integration, so it reduces the computational effort, but also it reduces the accuracy. Okay, I will show you the results afterwards. And now I move to the Gaussian quadrature method, where the idea is has some similarity with the WRT method. Well, here I am using a slightly different notation because it's for historical reason. I have been using here 0, 1, 2, 3 instead of 1, 2, 3, 4. Sorry, but basically it's the same idea. So we will be computing the nonlinear term for the first component, now called 0. But now we will be running the first integral over this component. No, for the WRT method, it was this one. Now we are running we are considering the first integration over the second one. Okay, the one with the same sign on the same side of this equality. And again, the last one is given by the delta Dirac function on the wave number. And I denote Ka, the sum of K plus K1 in terms of vector, and sigma A, the sum of sigma plus sigma 1. Okay. So as before, we obtain the last wave number from the three other ones. Okay. And removing the Dirac delta function on K, we obtain a fourfold integral on K1 here and K2. So this one and this one. Okay. Now I do some manipulation to convert the Boltzmann integral from the wave action density spectrum to the frequency spectrum expressed with the sigma, the intrinsic frequency, and the direction theta. So for that I use classical relationship, which in deep water write in this way. And when I substitute this in the integral, I get this expression with again the notation that W is the difference in frequencies. So sigma plus sigma 1 minus sigma 2 minus sigma 3. And of course, this should be 0. Okay. So here, now the next step is to remove the Dirac function on sigma. And okay, for that, I first introduce the ratio of sigma A or more exactly, the ratio of the sigma for the wave number Ka. So Ka, I recall you, is K plus K1. Okay, so the corresponding frequency is denoted sigma of Ka, and so I build the ratio of this over sigma A, which is the sum of sigma and sigma 1. Okay, they are different in general, these two frequencies, and so this parameter, which I call epsilon A, is defined as 2 times the square of sigma of the frequency of vector Ka divided by sigma A. Well, it can be formulated equivalently in this way, and it can be shown that this epsilon A is comprised in the range 0 to 2. And we can compute the associated direction of this vector Ka, which is given by this expression. And so we can reformulate W, so the frequency difference, under this expression, where here I have written sigma 3 as a function of Ka and K2, and similarly for the directions. Okay, so now we have to integrate the Dirac function, and so we use this property. I have been using the same property in the WRT methods. When you integrate a Dirac delta function in this way, the result is given here. Okay, and so here this is applied to the frequency difference, and the integral is running over θ2, and this allows us to remove the delta sigma function, but it gives rise to this term, which I call 1 over S, which correspond to this term. So this term is, well, given by this expression. It can be derived explicitly, so we have this expression. The problem with this term is that it may vanish. So S may vanish here, so it means that we have singularities in the numerical evaluation of this term. And here, so by doing this, we have reduced the integration over a threefold integral now running over sigma 1, theta 1, so this is for component K1, and sigma 2 for component K2. And here we have a sum over 2 discrete values because there are 2 directions theta 2 which allow to fulfill the resonance conditions. And they are given by, I don't know, I didn't write it explicitly.
To know if it is this S, 1 over S, S is really singularity, or it's integrable? I mean, what kind of singularity?
I will come to that. Yeah, I will. Okay. I will show you that. I will respond to that. Okay. Well, if we look at this at the expression of this S here, I provided the detailed expression. In fact, it can be written as a product of 3 terms: B0, B1, and B2, which I gave the expression here. So they are all functions of epsilon A, so the non-dimensional parameter I just introduced, and W2. What is W2? It's the sigma 2, the frequency of component 2 divided by sigma A. So it's also non-dimensional. So all these are non-dimensional parameters. And we will be looking what are the values of W2, what are the value of sigma 2, which allow to fulfill the which make this term vanish for a given epsilon A. So, as I said, well, this is the point where we are now. So we have this expression to evaluate numerically with this term, so the S term, which may have a singularity. Now we can see we have the threefold integral with a reduced range of integration for sigma 2, which is from 0 to sigma A divided by 2. And these are the 2 expressions of the direction of component 2, which appears, which are associated with this discrete sum here. Okay. So if we look at this term, so I don't have to go into all details, but if we look at each of these terms, it can be shown that B0 cannot vanish in this integration range unless Ka is 0. this B1, it vanishes only for a particular value of W2, which I call W2 minus, which is given by that. And for B2, there are two cases to be considered. The first one, if epsilon A is lower than 1, then it is always positive, so no singularity. And if epsilon A is larger than 1, then B2 can be written under this form, which shows that it may vanish for these two particular values of W2, which I call WA and WB. And if we restrict the integration range due to symmetry between these bounds, in fact, only one of these roots fall into this range, which is the one called W2A with this expression. Okay, so if I draw a picture, which is maybe more clear, so here along this axis you have epsilon A, which varies between 0 and 2, as I said before, and here you have W2. So due to symmetry consideration, in fact, the range of integration over sigma 2, so over W2, is restricted to 0 to 0.5. Okay, and so here you have this curve show you the value of the lower bound, W2 minus, which is a singularity for the term B1. And this blue curve show you the upper limit, W2A, which is also singularity for the term B2. Okay? So in fact, in practice, we have to integrate between the red line as a lower bound and either the light blue one for up to here, and then the dark blue one when we are here. So the integration range over sigma 2 is restricted to, as I said, as indicated with this arrow, to this range. And due to symmetry, we stop here at 0.5. Okay, and here are the, if I make slices at various values of epsilon A here, I choose 3 of them, 1.2, so above 1, to show the shape of this term, so which has 2 singularities, as I said, one here and one here. One for epsilon A equal 1, so 1 singularity here, and one for epsilon A below 1, which has only 1 singularity at this value. Okay, so this is a term we have to integrate. And for these singularities, as Miguel asked, we will be using Gaussian quadrature because it can be shown that the general form of the singularity, for instance, is typically of this form. Okay, and so it's convenient to use this kind of Gaussian quadrature integration because what is called here the weighting function here is of this form. So it corresponds to the form of singularity we have. So we have a numerical method of integration, which I will say take care exactly of the form of the singularity we have. In short, yeah, it's an integrable singularity. And so we approximate this integral, yeah, as I said, with okay, we approximate this continuous integral with a discrete sum of the value of the function to integrate chosen at specific nodes, which are given by the type of quadrature we are using, multiplied by weights, which are also associated with the type of singularity we are dealing with. Okay, so here is a summary of the integration. So regarding the integration of sigma 2, we may have either 1 or 2 singularities. So for this, we are using a Gaussian quadrature with NF2 points. It means that we will have NF2 values of sigma 2. And then there is a second integration over delta 1 here, this one, which also have singularities for the case epsilon A equal 1. And here we use a Gauss-Legendre quadrature, which is also suitable for this particular type of singularity. And it is numerically approximated using a number of points, which is called here NT1. And finally, for the last integral here, we are simply using the classical rectangular method because it appeared to be sufficient. So at the end, with the numerical discretization of each of these three integrals, the total number of configuration to be considered is a product of NF2, so this number of points, times NT1, this one, times NF1 from this integral, times 2, because we have the symmetry condition on θ2, as I explained. So this is a total number of configuration we will be considering in practice for the numerical evaluation. And here I show you three particular settings we have been using with the specific values of this number of points. And this is the corresponding number of configuration, of quadruplet configuration we get. So for the fine resolution, we have almost 10,000 configuration. We have a medium type setting with almost 2,000 configuration. And we have a reduced one, which are called raw or coarse, with about 800 configuration. You can see here that the medium and the fine, so the blue and the green are almost superimposed, slight differences here, and the raw makes a bit more difference. Okay, I have to move, sorry. So I have to move also. So we did a number of other improvement and optimization in the implementation of the method. In particular, we factor out and pre-compute all terms which do not depend explicitly on sigma and theta. And so all these computations are done once at the beginning of the computation, and then at each time step, the number of loops to be performed is optimized, benefiting also from the symmetry and scaling properties we have. I'm just finished. And one important thing also is that we have been using what I call a non-interpolating version. I mean, instead of interpolating values of the spectrum, we take the nearest bin. And in addition to that, we use a detailed balance principle introduced by Hasselmann, which says you that if you compute the nonlinear transfer term for component 1, for instance, you have it also for component 2 and for component 3 and component 4. And you store it for, for all the 4 components of the interacting quadruplets. And we filter out also configuration with a minor contribution. I have to skip that. And just to show you the results of the exact method. So this is the results from, again, on the same spectrum of the JQM fine method, the reference one. This is a comparison with the WRT method. You can see very similar shape of the nonlinear transfer term. And this is a result of the coarse JQM method, which looks also very similar. And this is this one from the reduced interaction method, which is an approximation of WRT, which saw basically the same signature of the nonlinear transfer term, still with larger differences. If we look at the directionally integrated term, we can see that both WRT and JQM with a fine resolution approximate very well the exact calculation, so the blue and the green. The blue and the red, sorry. The green one, which is the coarse calculation of JQM, also does a good job. And here we have larger differences with a reduced interaction approximation. Okay, I will skip that. Just show you this animation, if it works. No. Just to give you what using the result of, I don't have the pointer.
It's here. Look at the screen. Yeah.
If I click on it, does it start or not? Okay. And here. Okay, no. Well, this was an animation of the turning wing case, which shows different behavior between these three methods, the DIA, the MDIA, and the JQM, where the nonlinear features are different, and in particular, in some case, you have bimodality with the exact method, and you don't have that with the DIA. Okay, I will skip that to conclude. Say just a few, just a word on CPU time. Back in 2010, we have CPU ratio for the GQM raw method compared to DER of about 25 when using the it in 1D simulations. But in recent years, when this model was implemented and used in modern wave models like WaveWatch 3 and Tomahawk, we get a ratio of CPU time in the order of 8 to 10, as Fabrice mentioned in the introduction. On our side, we are getting a factor of about 10 to 15, but we are still testing that. So there is a room to improvement, maybe to reach in a couple of years factors lower than that, maybe 5 or maybe less. Okay, and I conclude here with this conclusion.
Okay, thank you very much.